Lesson 323, Area Under the Curve, Part 2. So we're going to still look at approximating area under the curve, but now we're going to look at left endpoint and right endpoint rectangles and use sigma notation to express their approximations. So in the last lesson, we looked at drawing different shapes under a curve to approximate area. Today we're going to look at a little more formalized technique for doing that. So we're going to start by graphing x squared. And we're going to look at the area under that curve for the interval between 1 and 3. And we're going to divide that interval into 4 equal subintervals, or essentially draw 4 rectangles under that curve. So if we take a look at graphing that function, creating that table to get key values inside that curve, and looking at the questions in problem 14, the y value of each coordinate, so if we start to look at points on this graph, we have the point 1, 1. We have the point 1.5, 2.25. We have the point 2, 4. We have the point 2.5, 6.25. So we can make rectangles from those key points. So in each of these rectangles, the y represents the height of the rectangle. And since we broke these into equal intervals, we have the interval of 3 minus 1, and we want to break it into 4 equal pieces. The width of each rectangle is 1/2. Subscript notation is going to help us label points on this graph. So if we look at the x coordinates that are important in this graph, we have x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So it's left endpoints on each rectangle. So subscript notation, we learned in an earlier section, is used to represent various values on the interval. So again, we're going to label those x values using subscript notation. And the 4 shaded rectangles in the diagram are called left endpoint rectangles because it's the left edge of the rectangle that touches the curve. So if I want to approximate the area under the curve by writing and evaluating a sum for the total area of the shaded rectangles. So I need to go back to my rectangles and find the area of each rectangle and then add those areas together. So the area of my first rectangle, length times width, plus the area of my second rectangle, length times width, plus the area of my third rectangle, length times the width, plus the area of my fourth rectangle, length times the width, or base times the height of each rectangle. So the sum is 6.75 square units, and it is less than the actual area, because if you look at this graph, I'm missing some pieces under the curve. So I'm approximating an area that's less than the actual area. So now we're going to look at the exact same graph, but we're going to move our rectangles. So we're still going to use 4 rectangles. We're still going to evaluate it on the same interval. We're still going to use the exact same curve. But now I'm going to use what's called right endpoint rectangles. So as I start to draw out my rectangles, I'm actually drawing my rectangles above the curve. Oops. So again, in each rectangle, the y represents the height of the rectangle. And this time, if I start to label my values, I have x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. But now these are called right endpoint rectangles because in each rectangle, the right end point of the rectangle is what touches the curve. So now if I'm going to approximate the area using right endpoint rectangles, I have to find the area of each rectangle and add those 4 areas together. Sorry. So now I have the first rectangle has a width of 0.5, but now a height of 2.25. And my second rectangle has a width of 0.5, but a height of 4. And my third rectangle has a width of 0.5, but a height of 6.25. And my last rectangle has a width of 0.5, but a height of 9. So when I add those areas together, I get 10.75 square units, which is definitely greater than the actual area under the curve. And you can see why this is true, because I have pieces of my rectangle that actually go above my curve. So using right endpoint rectangles, I'm always going to get an area higher than my actual area. And using left endpoint rectangles, I'm always going to get an area a little less than my actual area. So looking at problem 16, the left endpoints gave us an underestimate of the actual area, and the right endpoints gave us an overestimate of the actual area. So we can figure out which type of rectangle we want to use based on the shape of the curve. Or we can determine if we have an underestimate or an overestimate based on the shape of the curve. So looking at the graph of x squared over this interval, it is an increasing function. It looked like that. So which type of rectangles produced the underestimate of the actual area? The left endpoint rectangles. And that's because each rectangle was completely below the curve. So where is a right endpoint rectangle going to produce an underestimate? In a decreasing function. If I had a function that looked like this and was decreasing, and I used right endpoint rectangles so that my right endpoint was touching the curve, here my right endpoint rectangles are going to give me an underestimate. So when evaluating area under a curve with an underestimate and an overestimate, what can I do to make these approximations closer together? One option might be to average the values. I could use more rectangles. The smaller the rectangle, the closer I'm going to be able to draw a rectangle to my curve, which will give me a better approximation of the area. So if I'm again going to take that exact same curve and exact same interval, but now I change the width of the rectangles. So instead of 4 rectangles underneath, I have 1, 2, 3, 4, 5, 6, 7, 8 rectangles. So I've changed the width of each rectangle to be 0.25. To find the height of each rectangle, remember that the height of each rectangle is the y value. So if I make a table with input and output, and I put a 1 into my function, I get out a 1. If I put a 1.25 into this function, I get out a 1.5625, and so on, inputting x values to calculate the y value. These give me the height of each rectangle. So if I want to approximate the area of this function between the interval of 1 and 3, using 8 rectangles instead of 4, I can again take my width times the height and take the height of each rectangle I have a sum of areas which add up to be 7.6875 square units, which is a closer approximation of that area under the curve. Tomorrow we'll look at how to take this sum and write it in sigma notation. Homework for this assignment is problems 122 to 127 and problem 129. Have a great day.